So instead of straight away going to derive the Coulomb's law, I will rather have some more explanation about this equation. F is equal to capital G m1 m2 upon r square, and in the sense that I will try to explain it to the system wherein we will try to understand what is the small g, the acceleration due to gravity, explain what is acceleration, etc., and build up the subject. So the equation that we had obtained for a system of two masses was the force F, which is equal to the universal gravitational constant m1 m2 upon r square, wherein this is the universal gravitational constant, the two masses m1 and m2, and the separation between the two of them. Now, for example, we can, if you remember, if you go back to another formula, recall it, that F is equal to ma, where a is the acceleration. A is acceleration. This is acceleration. This is from the kinematics, that we define the acceleration A as time rate of change ddt of the displacement, which is the time rate of change of what we call the velocity. V is velocity. Right now I am not explaining to you that the velocity and acceleration are in fact vector quantities. Both of them are having magnitudes as well as direction. So A is defined as the rate of change of the velocity. Now, this acceleration could be constant and could be a function of time again. But here, the acceleration that we take is taken as a constant. It's not changing with time. So, and this is a manifest of Newton's second law. We can also write this as F is equal to m dv dt. Okay, so F is equal to m is also a constant here, m dv dt, rate of change of the velocity. And because this m is a constant, I can take it up as inside and write it as ddt of mv. Now recall that this m into v, this is called momentum. So I can write this as equal to dp dt, where p is equal to mv, the momentum. Which is the product of the mass and the velocity of any object. Now, I can write, now this is the form again of the same Newton's second law which we can obtain, and because this V, we can also write this V as equal to rate of change of d dt of the displacement x. The displacement x, and I write that x is displacement. So I am going the other way. Normally we define first of all displacement, then velocity, then acceleration, and here what I am doing is I am introducing the acceleration, introducing the velocity, and then introducing the displacement, which is the displacement also is a vector. So all these quantities I can write as in vectorial connotation that this is vector A, vector V, and vector P, also vector X, which all of them have the magnitude as also they have direction. So here, looking at this, if suppose we take the system, and the system that is introduced to us in the beginning is the system of the earth. Earth we take as a round object, and we can say that with all the mass of this earth is concentrated at its center. Of course, this will happen. The mass of the earth is m, and suppose then I have here, for example, in Aligarh or anywhere wherever you are sitting, there is another mass which is small m. Now this small m I can vary, and then we will have a force of what we call gravity. This will be a force towards the center of the earth. But there is a very interesting thing, and that is this force cannot exist all by itself. So there has to be another force, and in the direction opposite to it, and this is the force F. I would like to elaborate a little bit like I did before, that this F is actually force on the body M due to body small m, and this is the force on the body small m due to the body capital M. So the body which is exerting the force, okay, its name we always take in the end, the second term, and the first term is the body on which the force is being exerted. Of course, the two forces are equal and opposite, and therefore I can say that the force mm and the force m small m, magnitude wise they are equal to each other, and this I can write as, suppose, the force F, say, मान लिया, say. I am still continuing from there. So we find that in this system I have the distance of the object given by r, and this r is, you know, it's a very large separation. So this mass is small m, at your place is away from this, the total Earth's mass concentrated at the center, okay, and the distance is r, and this mass that we have here, I can say that this mass is a variable. So if the mass is variable, then this force also becomes variable, which depends upon this mass. So I can say that in this case, in this simplified case, in the case that we have taken of the Earth and a mass system, that would be in grams, kilograms, doesn't matter, because the mass of the Earth is too much as compared to the mass of the body under consideration. So I can write this again as, so in this equation that we have, I can put up the values m, small m, and r square. Now we are talking about the Earth as a system where we live in, okay, and here you find that because we cannot change r, we can of course, but here on the surface of the Earth we will consider that r remains almost the same. The mass of the Earth, which also does not change, capital G of course is a universal constant. So I can write this equation in the following format: capital G m upon r square together taken as a constant multiplied by small m, where this small m is a variable. So you can see that I can write this as capital G m upon r square, like in the text, as small g into m, where small g is equal to capital G m upon r square, and if we compare these two equations, f is equal to ma and f is equal to m into g, so or dm, so this appears to be another constant, and this is the acceleration due to gravity, acceleration due to Earth's gravity. But here I will not, I am not writing Earth because it is understood that we are on the system Earth, and therefore we can write like this, capital G m. So this is the acceleration, and the unit of acceleration, unit of g, is the same as unit of any linear acceleration, unit of linear accelerations. So I am being naughty. Linear acceleration, and which is, and this unit is meter per second square, meter into second minus 2, which I write as meter per second square, or like my teacher used to say, this is meter per second. This used to fascinate me in those good old days. What is per second? So meter per second or per second square, unit of g, the same as that of any linear acceleration. I said I am being naughty. and I am being naughty because I have introduced the term linear. So you must know when there is a term, a special term and adjective has come. So that means there are other kinds of accelerations also other than this linear acceleration. So unit of g is meter per second square, and therefore I can write that from here, of course, the unit of f is, unit of f as we know is kilogram meter per second square. Kilogram meter per second square, and this unit is also known as Newton in the MKS system. See, I am writing Newton with a small n, but here the symbol is capital N. So it always happens in most of the things when the units are taken. So be careful that units are like that. So we get G is equal to capital G M upon R square. And if we substitute the values of known values of capital G, capital M and R square, as also we determine it experimentally. The value of G is determined experimentally with the help of a very simple experiment which is called the pendulum. So simple pendulum. So this turns out to be approximately 9.8 meters per second square. I'm now using the slash for the first time, which in estimation problems, when we have estimation problems, then we must take this as approximately 10 meter per second square. There will be occasion later on when I am teaching you, not this, this is only an introduction to the multiple system of variables. But when I take up this, then how the value of G changes with height, with depth, what is the value at the equator and what is the value on the poles and this and that. So that kind of an analysis will be there. But right now the capital here, suppose I, instead of being or placing this mass on the surface of the earth, now let us take the system the same as the nearest object that we have to the earth, Chandamama. If we instead are at the surface of the moon, so this mass is the same, it will not change. Of course the capital M will change, capital R will change, and in that case we can introduce, I am writing for you that the value of the G on the moon, this will be equal to capital G mass of the moon upon radius of the moon squared. Okay, so that there are many questions where if we substitute these values, the value of G moon turns out to be approximately 1/6 of the value of the G on the surface of the earth, and then the objects appear to be lighter, and then if you want to jump on the surface of the moon, then you can jump more distance for the same angle, for the same projectile, etc., etc. We'll just after this introduction, for now I am going to stop. here, and I want you again to probe. The probe. There are two words I want to introduce today to you. You probe. 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 And the other word is, which I like more, is ponder. If you don't understand the meaning, look into the dictionary and you will enjoy that. The exercise that you have to do, the mental exercises which are required of you and which sharpen you. My whole purpose is just to sharpen you, just to use one thing in another situation. And while I close, I will just write a few equations of kinematics, which I hope that you will be able to do. One of the first equations is V is equal to U plus AT, a linear equation. Okay? For A is constant and U is also a given value. And then what we have from before, which we can write there, that S is equal to ut plus half at square, and v square is equal to u square plus 2as, and of course in all these equations a is constant. Constant not in the sense of pure constant, but a does not change. This is the case of constant acceleration, where you can derive these set of equations. The symbols have their meanings. You know, if you, and of course for the beginners, I will in a nutshell, and the next something, I'll use these things to make more inferences, and of course here the a is constant acceleration. V is the final velocity, use the initial velocity, t is the time. Okay, so we can have the constant is that there is an initial velocity, the result is that there is final velocity, and the time is changing. So this is also written as in some of the text these days, that this is x minus x0 is equal to ut plus half at square. The separation that has been taken are what we call the displacement. So next time you are supposed to be, still this is this is linear system, this is a non-linear system, 2 is a non-linear system, and we'll arrive at it and discuss these things together to probe you. I want you to probe into the matter, and I want to ponder, to analyze and synthesize the things to your benefit, and this thing sharpens you. So meet you again sooner and talk about the one thing I would like to say. In these equations there is no mass factor. So these are the equations of linear equations, I mean linear systems, I mean simple motion system where there is no mass. So these are the equations which are called kinematics, kinematical equations, not kinetic equations. Because in kinetic equation the factor of mass comes, the dimensions of time and displacement. These are the two dimensions only, how time is varying, this, that, but there is no any factor of mass. Of course, we can relate that with kinetics, in which the mass is there, There is no question of nothing like force, how it is related with force, etc., which we will talk soon, inshallah. Thank you.